Good morning. Here I present to you important method and results on computation of videos by direct equation. Here we list the properties of videos that make them a good model for cold fusion. These statements are demonstrated in previous works. Now we go give some simple arguments to support them. It is important to note that a femtoatom can induce a favorable interaction with a lattice nucleus, unlike a neutron activation and the consequences for transmutation. From Marianne Barbara works on anomalous solutions of Dirac equation, we computed ideal functions with a number and sets to connect the solutions inside and outside the nucleus, but did not allow us to have derivatives continuous at the junction radius, and the energy used to compute the value function was the energy of solution for point like nucleus case. Moreover, we could not evaluate the relativistic coefficient gamma and energy parameters as kinetic energy required for better understanding of ideas and possible interaction with nuclear fields. These imperfections are listed in the form of 3 problems. That is why we study the possible existence of ideas in a semi-classical way to better know their energy parameters. First, we directly address the Heisenberg relation as a starting point for a neutron confined in a sphere of radius r. For the quantum probe P, we can compute the relativistic coefficient gamma by the expression involving the reduced quantum equivalence. At ICCF 21 and in the paper of proceeding, we gave examples showing the expression of gamma give realistic values. We can see electrons confined in deep orbit are highly relativistic, but a strong relativistic correction to the Coulomb potential can confine such energetic electrons. In order to find ideas, we look for a local minimum of energy of electron in a central potential obtained by a balanced combination of electromagnetic potentials near the nucleus. Recently, we took relative corrections into account, especially the lamp shift, where the effects become very strong near the nucleus because of the strength of the electric field. We expressed the lamp shift as a repulsive quasi-potential by means of extrapolation from data tables on QED effects on orbital parameters. Here we plot an example of local minimum of energy. These semi-classical studies provided a lot of useful information for correcting the imperfection of the initial solutions of the Dirac equation. Not only we can evaluate the gamma coefficient, but also all the energy parameters. Moreover, we found that the relativistic Weyl theorem was respected by ultra-relativistic ideas in a very simple form and for various combinations of potential. This allows to deduce all the energy parameters of the Dirac videos computed as a mean radius of the probability density distribution and to check their coherence. Now we show how to apply new information to Dirac videos. But first we give a very brief theoretical local about resolution of a quantum differential equation. In fact, this problem includes 2 concomitant mathematical issues: to solve a differential equation and to solve a spectral problem for finding eigenvalues associated with solutions of differential equation. We have to solve radial differential equations where the radius R belongs to 2 distinct domains of the real numbers associated with inside and outside of the nucleus, respectively. And the central potential are very different in these domains. This implies the formal solution have to be expressed in piecewise form. On the other hand, Maple can solve a differential equation on a limited domain. Here it will be the outside of the nucleus. For the Dirac system of radial equation we observe. First, the formal solutions are very different in the two domains and they are very difficult to unify. Secondly, the solution on the considered limited domain is formally the same as the overall domain of real numbers. Here, this letter corresponds to point-like nucleus case. So, the general solution for point-like nucleus case can be used for the domain associated with the nucleus outside. Here we indicate the general solution of system of Dirac radial differential equations used outside the nucleus. But some parameters of this function are in fact expression including the energy E, the eigenvalue of the Dirac Hamiltonian. While applying general solution to the limited domain outside a finite nucleus, we cannot use directly the eigenvalue associated with the point-like nucleus case. But we can solve this issue by an iterative method, looking for a fixed point to stop the iteration. Before the fit point process, we consider the question of connecting the codes of inside and outside the solutions as a nuclear surface with continuity of total function and their derivatives. For doing this, we found a mathematical trick allowing us to simulate an answer with 4 free parameters, while restoring the initial coupling between the two components of the general solution. We do not give the different steps. They are simple but a bit tedious and time-consuming to develop. The iterative process is indicated here in the very simplified form. For a given value of radial quantum number, the expression of the energy for the solution in the point-like nucleus case gives the value E0. At step 0, we take E0 to determine the wave function and we compute the electron probability density. Then we deduce the mean orbital radius R0 and we directly calculate the total energy E1 at R0. Next we go to step 1 where a new value R1 of orbital radius is computed. Finally, we can stop the iteration at the step 1 where the fixed point is practically reached. Here we plot the curve for probability density corresponding to values 1 and 2 of the radial number. We indicate the values of gamma and kinetic energies not obtained in the initial solutions. We give also the new total and binding energy and compare them with point-like nucleus case in orange. Moreover, one can verify the mean radius and the total energy certifies the relationship given in remark under the chart. This property is deduced from semi-classical studies. Finally, we observe the shape of curve is similar to orbital 1s of regular solution. Here is a first attempt to evaluate the possible population of idiostate by tunneling from ground state in the form of superposition of quantum state. We consider two antagonist interactions, one due to the attractive relative effective potential and the other to the Eisenman relation, increasing the kinetic energy to prevent the containment of electrons. We call it Heisenberg barrier. We plotted the curves for semi-classical energies. Note, these are not static fields, but dynamic effects associated with an increasing confinement of the electron. We can say that eigenumeric barrier is a virtual dynamic barrier. To compute the secret tunneling, we use the WKB approximation in dimension 1, similarly to the calculation of Gamow astrophysical factor. The values on the vertical axis of the graph are multiplied by the power of 10. The integral of k corresponds to the blue R below the curve. Note that tunneling effect is extending here to the dynamic barrier, which is not usual. We obtain a reckoned amplitude of wave function in ideal zone and an estimate of probability of ideal state. The general wave function of basis state for atom H could be a linear combination of ideal and good state. Of course, it would make more sense to use a WKB approximation in DIM 3, but it's much more difficult to do. And for the time, some trades have given rise to bad or non-credible results. In conclusion, we emphasize the high energy of the ideals, which is very useful for acting in particular domain. Here we indicate some questions and ideas for future work. For the important problem of populating ideals, a possibility is look for physical parameters in condensed matter, allowing to increase the tuning indicated previously.
Now already some questions.
Many years ago, and you mentioned the work of Malley and Vavra, there was a response from Young Kim at Purdue in the papers at the time that these solutions, while they were actual solutions to the Dirac equation, they did not manifest in reality. That these physical states were never populated in the real world. Subsequently, Jerry Vavra tested a number of his own experiments, tested to try and find these states of shrunken states of hydrogen, I believe in particular, and could not find them. In your work, have you seen anything that would allow us to detect whether or not these states are real or if they are just an imaginary solution of the Dirac equation?
What means imaginary solution?
A solution that you don't find in nature.
It's a problem to detect because the probability, presence probability is very weak, and there is a very weak influence on the wave function. Effectively, we have two things about whole process to detect the little difference on the energy of electron caused by the superposition of quantum state. There is another word of the name Deck and physicists I'll make a publication on the possibility of superposition, quantum superposition of state due to department, but in other manner to calculate with Whittaker's equation. And they conclude with much more weak probability because they don't use tunneling. But there is a very weak effect to detect with spectroscopic method. Because I don't know, it's very recent, this part of the trial, of the work. And I did not yet compute the stability of this superposition, quantum superposition. And it's possible there is a association between the superposition and the unused state, the gold state, the normal and another. Because I have to calculate the lifetime of but the golden rule is difficult to apply in this case. It's not the good condition to apply the golden rule. I cannot yet answer your question, in fact.
Well, some other question maybe, Jörg?
Yeah, we know that we know that these equations have a very...
Sorry, we can't understand you. Don't speak.
I use a microphone. Okay. We know that these equations work very well at the Bohr level because there is a very good match between the Lagrangian, the mechanical Lagrangians, and the quantum mechanical Lagrangians. But if you depart from the Bohr level, there is asymmetry. The magnetic forces get much stronger and the electric forces increase less. So what I expect of you next time you present such stuff here, that you present the correct force equation for the orbits first. There is no force equation in this formulation. It is fantasy. You cannot show that we can keep 120 MeV on an orbit on this level. It's just nonsense, you know. Please show me the force equation that is able to bind 120 MeV of energy on an orbit. A physical force, not just a fantasy distribution of an orbit.
Well, it's becoming very specialized. I guess you have to sit together with a piece of paper to make sure you understand each other because like that.
What is exactly your question?
It's hard to understand what you mean. Sorry, maybe you have to explain.
Yes, we have to discuss.
I guess. But would you have a dream to test this theory, to make some experiments to test this theory?
Yes.
How should we make such a test? You know?
I did not think to the test. I have to take this very recent and not the time to imagine to think.
Yes, you mentioned that the electrons were highly relativistic. I was wondering if you could quantify that. Exactly how much more massive did the electrons become in their relativistic state?
Les électrons deviennent plus massifs.
They are very relativistic. Gamma. Gamma, for example, for quantum radial number 2, gamma is equal to 400. It's very high. Very I in energy, kinetic energy, 2 not approximately bigger electron volt. For me, I don't. The notion of mass is not. I think you speak about the concept of relativistic mass, but I don't reason with this concept because there is redundance and confusion and redundance when consider the relativistic mass because we can in kinetic energy the relativity include in fact the kinetic energy. In consequence, I don't think that the electron become heavier. For me, in my concept. But I can